Welcome back, everyone. This is Professor Herring. In this video, we're going to learn about molecular polarity. To understand molecular polarity, we need to understand the valence-shell electron pair repulsion model and how it gives us the molecular geometries, and also trends in electronegativity. So this is combining information from the beginning of Chapter 8 and Chapter 7. We'll use that then to establish whether or not molecules have overall dipole moments, or net dipole moments. And it turns out that molecular polarity is a vastly important topic. It has huge implications for how our world works. If you've ever made mayonnaise or used butter or any variety of commercial products that have some components of water in them, then the polarity of water has come into play in terms of how they function and behave. And so it's really important to understand the idea of molecular polarity because it has huge implications for reactivity of molecules. Let's begin. When we talk about a polar molecule, we're talking about a molecule that has a net charge separation between two ends of that molecule. So there's a negative end and a positive end. In order to have a net dipole moment, or a net dipole, it needs to have polar bonds and a geometry where the bond dipoles do not cancel. Remember here we talked about the differences in electronegativity from Chapter 7, and that's what we're going to be applying here. To determine the polarity of a molecule that has more than two atoms, we need to follow a couple steps. Before we do that, let's talk about if there are just two atoms. Because if there's just two atoms, then remember, we've determined that it is always going to be linear. And then all you need is to determine whether or not there are polar bonds. And if there are polar bonds and it's linear and there's two atoms, then it's a polar molecule. It gets a little bit more complicated when you've got three or more because those bond dipoles can cancel each other out. The first step you want to do is draw out the Lewis structure. So let's say that we're trying to determine the polarity of water. We're going to draw out the Lewis structure of water and predict its molecular geometry. In this case, we see that water has 4 electron domains, 2 bonding and 2 non-bonding, which means that it's bent. Then we draw in the bond dipoles. And when we drew bond dipoles before, we drew arrows with a positively charged tail and a negatively charged head pointing towards the more electronegative elements. And you'll have one arrow for each bond. Then we can determine whether or not those bond dipoles cancel. And this is why it's important to draw it properly in 3 dimensions. Because if you're tempted to draw water like so, and you draw the bond dipoles, then we actually see that they oppose each other. They're equal and opposite direction, and so they would cancel. But in reality, water is a tetrahedral overall shape, bent molecular geometry, and so its bond dipoles, when we add them together, they produce a resultant bond dipole, which means that the molecule is polar overall. And indeed, when we do studies with water, we see that water behaves like a polar molecule. You can see in this map of electrostatic potential that you have the partial positively charged region and the partially charged negative region. Let's look at some other examples. Carbon tetrafluoride, is it polar? First step is to draw the Lewis structure and predict the molecular geometry. This is a tetrahedral electron domain geometry, tetrahedral molecular geometry. We draw the bond dipoles and then predict whether or not they cancel. This can be a little bit hard to see in 3 dimensions, but it turns out that these cancel each other. And we'll talk about a little bit later about which of the molecular geometries will, in general, cancel each other out. And so there's no net dipole here. For ammonia, we do the same process where we draw its Lewis structure and predict the molecular geometry. It also has 4 domains, but one of them is bonding. which means that it's going to be trigonal pyramidal. When we draw the bond dipoles, we only have 3 bond dipoles. There is no bond dipole between the nitrogen and the lone pairs because it's not a bond. Therefore, there's a net dipole pointing upwards. The 3 bond dipoles cancel going from left to right, but nothing is canceling out the upward direction of those dipoles, which means that we have a net dipole. And indeed, when we look at the map of electrostatic potential, we have a partial positively charged region and this is partial negatively charged region near the nitrogen, and partial positively charged region on the other side. Notice in this map of electrostatic potential up above that there are differences. We do have negative and positive regions, but there's no end. In other words, they're not on opposite ends. It goes from negative to positive back to negative, and they cancel each other out. So go ahead and try this problem on your own, and then I'll walk you through it. Pause the video now. Welcome back. So you should have drawn these Lewis structures for our molecules here. We can see that they're all electron domain geometries. They all have electron domain geometries that are tetrahedral, and they're all tetrahedral for their molecular geometries. However, when you look at the bond dipoles, they're different. They cancel out in the case of carbon tetrachloride, but the bond dipoles are essentially non-existent between hydrogen and carbon. Therefore, that gives us net dipoles on these other molecules. Remember that when we're looking at Lewis structures, those are 2-dimensional. But when we look at the 3-dimensional Lewis structures of our molecules, we can see that we would never be able to have the chlorines cancel each other out. They would have to be 109.5 degrees approximately away from each other, which means that there's going to be a net dipole pointing off in one direction. And then the last one is actually rather easy. There's only one net dipole because there's only one polar bond. And so it turns out then that 2, 3, and 4 are the polar molecules. We can look at organic molecules as well and determine polarity. So looking here at which of these are polar, if we draw the bond dipoles, then they cancel out in this molecule. But the bond dipoles don't cancel out in the molecule on the right. And the reason for that is just the physical orientation of those elements and where the bond dipoles point in space. Okay? Why don't you try this one on your own? Pause the video and see if you can figure this out and determine which of these are polar or not. Welcome back. So if we draw the bond dipoles, they're pointing from the carbons to the chlorines, which gives us a net dipole in the resulting direction. We can repeat this process for all of the molecules. And what we see is that when they're exactly opposing, or when the net of them is that they're opposing, then they cancel out. And sometimes it's easiest to draw this from tail to tail, tail to tip. When done this way, you can see that they essentially go back from the starting place, starting place and the end place are the same, which means that there's no net change. If we were to take a look at the bond dipoles of these other molecules, we can actually see that there's a difference. Try to draw them the same length when they're the same elements that are involved. And what we can see in this case is that the length of the resulting bond dipole is different. In other words, we can make a qualitative comparison and say that this is more polar than the other molecule, whereas these are equally nonpolar. The last thing here is to summarize molecular geometry and molecular dipoles. The steps you want to take are draw out the Lewis structure, then use VSEPR to determine the electron domain geometry, and the number of bonded atoms to determine the molecular geometries. Then, using the molecular geometry with the differences in electronegativities, you could determine the polarity of the molecule. And what you'll notice is that there are certain molecular geometries that will always cancel out if the exterior atoms are the same. And that's very important. So the caveat to that then, so tetrahedral molecular geometries always cancel each other out, assuming that the elements are the same. But if they're not the same, then they don't cancel out. That's it for this video. Thanks for watching. If you have questions, ask on Piazza, in office hours, or in recitation. Have a good day.